现在声音有没有好一点？
有哦
Thank you.
可以吗？
可以。
啊，OK，那我们就开始了。Jack, so you will answer the question when we get to it.
Please go ahead. Yes.
OK，等一下啊。这样可以吗？我们可以开始吗
Yes, please.
Andy, OK. All right, let's start. First, we go over the questions. 5 questions. First question is about the coefficient in front of the inversion charge density for the mobility model. Okay. For half, the factor half in front of the Qi for the electron mobility is to refer to the center of the inversion channel because if okay, so this is the effective field. If it's total charge, okay, Qd plus Qi, then that's the effective field at the surface. Okay, with the half factor, that means that the effective field at the center of the inversion channel. In other words, half a Qi from the surface. Of course, there's half a Qi and 100% of Qd after the center. Okay. So that's a physical meaning. But for the whole, this 1/3 is completely empirical. That's because if we use 1/2, that's like electron case, then we don't have a universal curve, like all these different doping would overlap together in a single curve. This only works for 1/3, and it's a little bit difficult to interpret what it means physically. You can use your own take your own guess, but that's where the 1/3 factor came from in the literature. Okay, next question is that's a basic one. Okay, this chart is for the non-GCA model is asking. Okay, first the x and y. Okay, x and y was defined on the first couple of charts in chapter 5. X is always in the depth direction, and y is in the source and drain direction. So the gate effect is in the x direction, but the current flows in the y direction. Okay. And okay, so for the GCA model doesn't have the y curvature term. Okay, only the let's see. Okay. So for gradual channel approximation at GCA, the 2D Poisson equation is solved in terms of 1D. In other words, we remember that in chapter 4, we solved MOS, that's 1D. So the same equation is used in GCA model. We only solve the Poisson equation in the x direction. Okay, so we ignored the y curvature term. That was let's see. Yeah. So for GCA model, we dropped this term. Okay. And yeah, and then we solve that. But there's one thing is about the charge density. Charge density has a dependence on the electron density on V. V is the Fermi level or the electron Corsic Fermi level, which changes from the source to drain. We can see, yeah. So V is Corsic Fermi level, 0 at the source, VDS at the drain. So it's a function of Y. So that makes the charge density a function of Y. Okay. And that's why I say that the GCA is solved 1D Poisson equation, but in vertical slices. Okay, so for each Y, you have a V, and then you can solve the you can solve the 1D differential equation, just like in chapter 4. Okay. So going back to the first chart. Okay. So GCA model has no Y curvature term. Okay. Only non-GCA model has add a term here to consider the effect of Y curvature, okay, which is important in the saturation region. Okay, so that's this question. And let's see. Okay, the third question. 孙院长可以 address 一下。
Yeah. 上次课程就讲 CVD versus PECVD 这个 CVD 主要就是thermal 所以温度通常会高一点。那它的反应我们上次也讲过，要有一些 source gas 或有一个 transport， 对，到那个 wafer 那个表面，你要沉淀那个表面，然后再 surface reaction 所以这样子的一个process 通常是比较慢一点，但是呢，它的那个 stoichiometry 它的那个杂质或什么这些会排列这个电解会比较好。那电浆这个就是用 plasma 多加了一个能量就是 electric field， 然后电浆当然是那个高电场，让它会这些一些species， 所以多了一个能量，它这样子的话就不需要加高温就可以做一些裂解，做一些那个成分的这些反应，然后呢，在最好也都是很靠近那个 wafer 那个 surface， 然后反应出来你就叠在上面。那有些时候你叠的速度太快，或者它就会排列这些就不见得是最好的，所以它 quality 不见得是最好，但是它就是比较便宜比较快。另外有一个电浆的一个好处就是说，我们就讲到那个 high density plasma 的时候，那就是另外一个层次了那也可以做一些 etch 之类的，所以最关键的就是那个 plasma enhance 的最主要的就是多一个那个 energy， 让那个反应物的这个分解跟那个formation 都加速这个速度，但它有一些其他的功能可以利用所以我想这里面就是从一个 film quality 的需求跟 deposition 的一个 rate 还有当然就是有一些所谓的 step coverage 我们也讲过，制程上面当不是平的嘛，很多都是会有对不对？一定有那个 feature 高高低低的，那你 sidewall 正上方这个旁边的这个覆盖率 ，DVD 是会非常好，因为它主要是 surface relation。那 PE 的话就 不见得了，它就是反正deposition 速度也比较快啊。但是它也有一些其他的招数，你有电场，有一些你可以一边 deposition 一边 etch 就可以从 step coverage 从那个 gas fill 啦，我讲从 gas fill 来讲我想大概说明讲那个很多细节的话，其实也都在网络上或在一些也都可以查不到啊。Yeah, 好的 ，Yeah, please.
OK，我们继续。Okay, next question. It's about this chart. The V has a two side B. Okay. Two side B was introduced in chapter 4. So we go back to this chart, which plot the charge density, total charge, depletion charge, and fixed charge, and the inversion charge as a function of gate voltage, and also surface potential. So two side B value is here. Now, we of course notice that the QI has a threshold, roughly about here, 1.3. And before that, QI is not zero, but it's very small. After that, QI starts to go up. And this takes place roughly two side B. Okay, so that's why the two side B was used. Physically, we don't model, MOSFET model, we don't have to define a threshold voltage. For example, these two equations, very physical equations, and that's the behind those curves. There's no threshold voltage defined. Yeah? But for mathematical simplicity, we take a two side B approximation. So we say that roughly speaking, when psi s is below two side B, QI is negligible or small. Above two side B, it takes off. So that's convention. We use two side B, which is a historical choice. But it simplifies the equations because, for example, in this case, we talk about the linear region, and we have a two side B here, and then CKVT is two side B, and I end up with this dotted line, which is a good approximation to the continuous solution shown by the solid line. Okay. Let's see. Oh yeah, and then let's go back here. Okay. And so that's the two side B, and the other is the minus VBS. Minus VBS is essentially the reverse bias of the substrate. Well, if it's forward bias, VBS is positive. If it's reverse bias, VBS is negative, and it's two side B plus reverse bias. And that is we covered in chapter 4 also, that if a junction, if there's no bias in the junction, let's see. Oh, I don't have this chart. So this is a PN junction with a reverse bias. Okay, so this is like the source junction. Let's see. Okay, so if this, go back here. Yeah. So if you have a reverse bias here, essentially the source junction is reverse biased, okay, compared with VBS equal to 0. So in that case, the inversion instead of at the two side B is two side B plus the reverse bias. And that's where this came from. It's two side B minus VBS. It's essentially the reverse bias on the substrate if VBS is negative. If you forward bias, then it will go down, but usually we don't forward bias substrate. That will cause source junction leakage current when you forward bias. Okay. Last question is about the pinch off, beyond pinch off. Okay. So if you increase the drain voltage, will the mobility decrease? If so, why the current be reduced but saturate? Okay. First of all, in this region, it's not in the low field, rather it's high field. So usually it's velocity saturated. Okay. Near the source, the mobility is important, but here it's we'll cover velocity saturation in chapter 6, probably next week. But we can see that when it's velocity saturated, then velocity field relationship, instead of straight line, it saturates at about 10 to the 7. Okay. Now, for the low field, you can define mobility, that's omega region. But a high field, you can okay. High field essentially mathematically is given by this expression. Okay. Again, we'll cover that in chapter 6 next week. But basically, it says that if the field goes up, then if you define velocity over field, which includes this expression in the denominator, then it goes down. But the velocity goes up. So in other words, the current will not go down because current is mainly related to velocity, carrier velocity. So at high field, let's see. At high field in the saturation, in the pinch off region, beyond pinch off, even though the ratio of V over E goes down, but V is still going up. You can see that the slope is suffered because of velocity saturation, but the velocity is still going up. Okay, so that's why we don't expect the current to be reduced. In fact, it's hard to describe that in terms of mobility because it's in the velocity saturation region. Okay, so I think that covers all the questions, and we'll start on chapter 6. Okay. Chapter 5 is a long channel MOSFET. Chapter 6 is a short channel MOSFET. And because from chapter 5 we learned that if channel length decreases, then the drain current goes up because it's proportional to 1 over L. So that's good. The capacitance goes down because it's proportional to L. Shorter channel has a lower capacitance. This is total capacitance. Cox is the capacitance per area. Cg is the capacitance in farad. All right, so short channel device has a very faster switching speed because of higher current and lower capacitance. But there's a problem. It cannot be too short due to the short channel effect, or SCE. In one word, short channel effect is the effect of the source and drain, okay, which we have not considered in chapter 5, because for long channel, source drain are very far away and it's very little effect. But when the channel length is short, source drain close together, and then it will affect the current. And so in another picture, it's a very simple schematic. Is that when we have a transistor, it's a 3-terminal device, source and drain, that's terminal 1 and terminal 2. So the current, you apply voltage, and the current between source and drain is controlled by the third electrode, namely the gate. So the gate will control this barrier between source and drain, and therefore that controls current from the drain to source or source to drain. But when the channel length is too short, then the threshold voltage becomes sensitive to channel length and drain bias. Okay, and that's what we want to focus on in the first part of chapter 6. The second part of chapter 6 is velocity saturation, as I mentioned before. When the mobility times the field, or this is the average field, reaches 10 to the 7, then the long channel current, the long channel current model is no longer valid. This should be long channel current model, no longer valid. And then the IDS is not given by this simple expression anymore. Right? So that's the other. So there are two parts for the short channel device. One is the threshold voltage. It's a function of channel length. The other one is the velocity, because the field in the source drain direction becomes very high. Okay. So this is what we measured the results for pretty much any generation. And basically you measure the threshold voltage as a function of channel length. If it's a long channel, it's the constant, like what we learned in chapter 5, 2 psi b condition. But once the channel becomes shorter, let's say below 1 micron or 1.5 micron, the threshold voltage becomes lower. And also, there are two curves, low VDS and high VDS. High VDS means that the threshold voltage goes down even sooner, even sharper. And eventually, if you are less than, let's say, 0.5 micron, the threshold voltage can become negative. This falls off very abruptly, like a cliff. And once the threshold is negative, then you cannot turn it off anymore. It stays on all the time. Of course, that's not a very, that doesn't function well as a transistor. Because for a transistor, you want the gate to modulate the current between source and drain. Okay. So if we look at the two sort of 2D potential contours, you have long channel device on the left and short channel MOSFET to the right. Okay. Not the same scale, this is 0.5 microns, but the aspect ratio is the same. You can see that 1:1, vertical versus X versus Y, same thing here. You notice that so each of this is a constant potential contour. But it's it's two-dimensional in natural. Okay. So when we have a long channel, it's mainly one-dimensional in the middle of the channel, or a very large portion. But in short channel, it's mainly 2D because of the source drain effect. Source drain, any point in the channel is very close to source and drain, and so the source drain will have an effect in addition to the gate on the current. Okay, so that's the basic physics. And if we look at further, okay, if we look at a Venn diagram in the lateral direction, okay, so far from chapter 4 and 5, we usually plot the Venn diagram in the vertical direction, in the X direction. But if you plot the Venn diagram in the source and drain direction, it looks like this. for long source is here, drain is here. A is long channel. Okay, and so the gate, if you increase the gate, this potential, this barrier will go down, potential go up, which means electron barrier go down, and current starts to flow. But for short channel, for B, this is for the same gate voltage, okay? Same gate voltage for long channel and then for short channel. You can see that the potential is even higher. In other words, the barrier is lower in the shorter channel device because of the effect of source and drain. Okay, and we can also see that in the measured current. Here's the measured current, drain current versus gate voltage for 3 devices. Long channel 2 micron, short channel 0.35, shortest is 0.2. So with and each channel has 2 bias, low drain VDS 50 millivolts, high drain VDS equal to 3 volts. For long channel 2 micron device, the drain voltage has no effect on substrate current. So we focus on the substrate current. And that's what we learned in chapter 5, the substrate current model. It says that once VDS is 50 millivolts or above, the current is not sensitive to the drain voltage. But that's long channel. If you reduce to 0.35 micron, first of all, you can see that the both low drain and high drain curve shift left, which means lower threshold voltage. Okay, just like indicated here. For the same gate voltage, the barrier is lower, which is same thing as saying that the threshold voltage of the 0.35 micron device is lower than the 2 micron device. Furthermore, there's a high drain bias and low drain bias. Now we have a difference. Okay? And this is so-called drain-induced barrier lowering. Okay? If you use this schematic diagram on the left, if it's long channel, you change the drain bias, change VDS, you change the drain bias. It doesn't change the barrier. But in the short channel device, if you further increase the drain voltage, which can bring down the barrier, and therefore the threshold voltage becomes even lower in the high drain bias case. And this is so-called DIBL, stands for drain-induced here. DIBL, drain-induced barrier lowering. Okay? That's the dashed curve here. Now, if you go further to the third device, 0.2 micron, which is even shorter. So VT shift, and here the high drain, the VDS has a very pronounced effect on the current. Okay. And in fact, even the slope has changed. Okay. At the 0.35 micron, the subthreshold slope or inverse subthreshold swing is pretty much the same as the long channel device. But once you go to 0.2 micron, the slope has changed. This is an indication. This is a reflection of the gate. Okay, gate is losing control of the current. Okay, if you have a sharper, steeper slope, that means gate can control the current exponentially, essentially. But once you have 0.2 micron and VDS equals 3 volt, then gate is losing control essentially to the drain. Okay, so the current is now, instead of controlled by the gate, is partially controlled by the drain. And if you go further, then the current will persist, even go to very negative gate voltage. In that case, we call it punch through. Okay, so the gate is completely losing control, and the current flows actually in subsurface. You can no longer turn the device off. Okay, so that's a problem we need to avoid. All right. So to model the short channel effect, we consider this so-called simplified geometry. Okay, so basically we have the source and drain, N plus dark green, and the gate is N plus for N-channel device, and this is the oxide, T-ox, and that's the diffusion width. Assume that the doping is Na, p-type in the substrate. Okay, so this wide region is the depletion region. In the depletion region, there are essentially no mobile carriers. Oxide, of course, is also insulating. The other colored region are like conductors. N plus source, N plus drain. Those are two conductors, left and right. On the top, you have the gate conductor. At the bottom, you have neutral substrate. So this is depletion region. Beyond depletion region, this is not depleted. So the mobile carrier here is a host, a p-type substrate. Now, of course, we look at the depletion region of the junction and the gate. They are combined together, and it's very, it's not in a regular shape. It's hard to solve. So we simplify it by considering this rectangle here, okay, instead of the actual shape. And so this rectangle, the left and right boundary are defined by the source and drain. Assuming that source and drain are very heavily doped, okay, and so there's not much depletion going on. And the top, of course, is the gate. The bottom is the we follow the depletion width here, okay, and so this gate depletion width. So this becomes a rectangle. Now we can solve the Poisson equation, because basically the short channel effect, to model short channel effect, we have to consider a two-dimensional Poisson's equation. Okay. And but the rectangular shape will simplify this so-called 2D boundary value problem, okay, in the 2D Poisson equation. But also we restrict it to subthreshold. Okay, above threshold is harder to model, because then you have a mobile charge. That's essentially nonlinear function, exponential function, and then you cannot apply superposition, as we will describe later. So we consider subthreshold region and simplify the MOSFET into this rectangle, and then we try to model that. Okay, so that's the rectangle, and so we describe a so-called a two-region scale length model. As I mentioned, we consider subthreshold current. So the charge on the right side, there's no inversion charge, only depletion charge. Okay. Furthermore, this rectangle has two different material. Okay. AFGH, that's oxide. Okay, so we call that potential psi 1. ABEF, that's silicon, a different dielectric constant. Okay, we call that psi 2. For the oxide, there's no charge. For the silicon, the lower rectangle, the charge is the depletion charge density, Na. Okay, subthreshold, so there's no inversion charge. Okay. So this defines the mathematical two coupled differential equations, and we need to specify four boundary conditions. And the four boundary conditions are specified by the four conductors: top, bottom, left, and right. Top is the gate. Okay, so gate is the psi. Also, we choose the origin to be here at to be point A. That's at the silicon surface or silicon oxide interface on the source side. Okay. And X again, it goes vertically, and the Y goes in the source drain direction. Right. So we assume that the oxide thickness is Tox. So the the gate is minus Tox because we define 0 to be here. Okay, and X goes positive in the depth direction. Okay, so gate is going up. That's minus Tox, and for right, so the gate is essentially minus Tox Y. Y can be anything that equal to the gate voltage offset by the flat band voltage. That this we introduced in chapter 4. And at the source region, source region is like a PN junction. Okay? So we have the built-in potential. Okay? And in this case, psi 2, because in silicon, the potential is assumed to be psi 2. And X0, that's AB. And on the drain is EF. Okay, so the XL, Y equal to L, is psi BI plus VDS. So it's built-in potential and also reverse bias at VDS. Okay, so those are three. At the bottom is the CD here. CD, the depth we define to be WD. Okay, 0 is A. Okay, WD at B is the diffusion depth. Usually the maximum diffusion depth near threshold voltage. Okay, so CD is this length, and that's 0. We assume that substrate, we use the substrate potential as a reference, and it's grounded to the source. Okay, so that's 0. Furthermore, we stretch CD to be the entire bottom of the rectangle, so it becomes B to E. Okay, because that makes it easier to solve these rectangular boundary conditions. Now, between psi 1 and psi 2, they are coupled by the dielectric boundary conditions. Dielectric boundary condition is X equal to 0, okay, Y between 0 and L. So, and so there are two boundary conditions at the interface, AF. The potential is continuous from psi 1 into psi 2. Okay? So every point, psi 1 equal to psi 2. And the field, the derivative, because this is Poisson equation second order. So the first order derivative is the field. The field in the perpendicular direction, as we covered in the basic 2D boundary conditions in chapter 2, is the displacement in the perpendicular to the interface is continuous. So that means the field in the oxide times permittivity of oxide equals the field in silicon, psi 2, times the permittivity of silicon. Okay? So that's these two couple the two equations together. Okay? So in general, we try to solve this simplified geometry and boundary value problem. And to do that, we apply the general approach. We make use of a superposition principle. In other words, we write psi 1 and psi 2 in different terms. And so that we can try to satisfy the boundary conditions one at a time. Okay, and but superposition principle, of course, only applies when the system is linear. That's why the subthreshold assumption is important, because there's no inversion charge. But once you are above threshold voltage, then you have an inversion charge in silicon. That inversion charge is exponential function of psi 2. Then you cannot apply the superposition anymore. Okay? So superposition technique and the method can only be applied in the subthreshold. But that's fine, because what we really want to know is to be able to model the threshold, the subthreshold region, so that we know how short the channel length can be, while still control the current in the subthreshold region. Okay. Now, so when we decompose that, well, we assume V1 and V2, those are long channel solutions. Right? Those actually we already know. We discussed in chapter 4 and chapter 5. Basically, this diffusion approximation, because it's below threshold, right? The only diffusion charge. And then, so that's the long channel solution. Then we add UL1 and UR1 for oxide potential, and UL2 and UR2 for the silicon potential. These two terms are added so that it will satisfy the boundary conditions, the two boundary conditions, basically the source and drain, left and right. The top and the bottom is already satisfied by long channel solution. But when we discuss in chapter 4 or 5 about V long channel solution, that will satisfy the gate and the substrate boundary conditions. Okay? But of course, long channel solution will not satisfy the source and drain boundary conditions. Okay? So that's why we add two terms for satisfying the source. UL1 satisfy the source, UR1 satisfy the drain boundary conditions. Okay? So left and right. And we write those functions UL1, UR1, UL2, UR2 in this form. Okay, now first of all, there are requirements. First of all, every one of these functions must satisfy the Poisson equation. Okay, and let's see, actually more like Laplace equation. This is called Laplace equation. So with right side equal to 0, this charge in the silicon in the psi 2 case is already taken care of by V2. Okay, because V2 is the long channel solution, this X solution in the in silicon. Right? And so that takes care of the diffusion charge. When you add more, these must satisfy the Laplace equation with right side equal to 0. Okay. That's why you have the sinh and the sine product on every one of them. And the underlying mass is this. Okay. So if you have a, let's say, a u function of sine kx, then you take two derivative of u. Okay. So you have k squared, and sine, one derivative becomes cosine, another derivative becomes minus sine. So there's a minus sign here. But if u is sinh ky, you take two derivative, sinh becomes cosh, and back to sinh with no negative sign. So for sine, two derivative gives minus k squared u. For sinh, two derivative in the y direction gives k squared u, and you add them to 0. So that's why you have the sinh and the sine product, and every term will satisfy the Laplace equation. We call it homogeneous equation with right side to be 0 because of this. Notice that sinh, so what's the k? K is pi over lambda here. And for sine, k is also pi over lambda. So k is the same. That's why this product satisfies the Laplace equation. Okay. Same thing for this. So everyone is the same k. Okay. And furthermore, we require that, for example, first of all, the top and the bottom boundary condition already satisfied by V1 and V2. So when you add UL1, UR1, UL2, UR2, those should not change the top and the bottom. So those four functions should vanish at top and the bottom. At top, top means minus Tx or psi 1. So you can see that that's why this is written as x plus Tx, sign of that. So if x equal to minus Tx, that's 0. Okay, so same thing here. Okay. At the bottom is psi 2, UR2 and UR2. And that's x equal to WD. When x equal to WD for psi 2, that's also 0 because that's sine WD minus x, so that's 0. And so is that. Okay, so this means that these four functions will not disturb the x direction boundary conditions at the top and the bottom. Okay, it's no effect. All we have to do is to focus on the left and right source and drain boundary conditions. Okay. So let's look at left and right. That's the y. Okay. UL1 is chosen to satisfy the source boundary conditions. So we want add UR1, but UR1 has to vanish at the source. That's why the UR1 has a sinh pi y. The source source means y equal to 0. Drain means y equal to L. Right? So when y equal to 0, UR1 is 0. So this will not bother the source condition satisfied by UL1. Conversely, when you try to use UR1 to satisfy the drain boundary conditions, UL1 will be 0 because UL1 has L minus y, so that's sinh. So if y equal to L, then the UL1 is always 0. Okay. Same thing for UL2. So basically, we add those, try to satisfy the source and drain boundary conditions without affecting the gate, the other three, the gate and the substrate and the drain for UL1. In this case, so UL1 is only in the four boundaries. UL1 is only non-zero at the source. At the source means y equal to 0. In that case, this factor is 1. UR1 is only non-zero at the drain, y equal to L. If this is L, this is equal to 1. So these four functions are carefully constructed to satisfy the boundary conditions. And there are coefficients. Those coefficients are chosen to satisfy the actual source and drain boundary conditions. That's the psi bi and the psi bi plus VDS. Okay. But first, let's apply the, we almost run out of time. Let's first apply the dielectric boundary conditions, okay, to these two solutions. Okay. it takes a little time to explain. So let's take a 20-minute break, and then we'll resume at 10:10 your time. The second period will end before 11 o'clock, so that 11 to 12 will be the time for the exam, and the midterm one, as I have announced. Okay.
OK，好，谢谢。
Okay, break. Okay, we continue.
Please.
All right. All right. We notice that in each of the sine and sinh, there's a lambda n parameter. Okay. These are actually k is pi over lambda for each case, so they have to be the same. But the value is to be determined, and these are actually determined by the dielectric boundary conditions. These two, okay, is shown here. So that's the oxide x equal to 0 is the boundary between oxide and silicon. Okay? So this is let's see. So when x equal to 0, this becomes sine pi tx. This becomes minus sine. No, this is pi wt. X equal, this is pi tx. Okay, and the potential has to be the same. And the other condition is the field times the permittivity needs to be the same. This is in the x direction. Okay, so these two conditions becomes the b1n. Okay, each term has to be equal because there are different functions. They must satisfy for every y function, every y values. Okay, along the channel direction, and so that's the potential being continuous across the interface. That's the field, the displacement, the epsilon permittivity times the field. The sine becomes cosine because of the derivative to get the field. Okay, now the trivial solution. The trivial solution is that, of course, b1n and b2n equal to 0, because these are two homogeneous equations. But we are not interested in that, in the trivial solution. So for non-trivial solution, that means you can take a ratio. That means the b1n, b2n are non-zero. So you can take a ratio and then they will drop out. So this equation, when you take a ratio of the two on both sides, then it becomes, this side becomes a tangent, 1 over epsilon oxide, and this side becomes, the right side becomes minus 1 over epsilon tangent. So we move the right side negative to the left side. So it becomes this equation. And this equation is what we call the eigenvalue equation. Okay? And this needs to be satisfied to obtain non-zero solutions. Now this equation for given thickness Tx and Wd, and given dielectric constant, of course epsilon oxide and epsilon silicon are fixed. Now actually only the ratio is important. We can solve for lambda, but there's an infinite series of solutions because these are trigonometry functions, so they are periodic. Okay? but they are irregularly spaced. Okay, so this has to be evaluated numerically. And so we call this lambda 1, lambda 2, and so on. In particular, we are interested in the longest lambda 1. Okay, and we call that the scale length lambda. Okay, because the longest lambda is the dominant term that's shown in the next chart. Okay. Right. So basically, if you look at the silicon, the 2D potential in silicon, psi 2, it has two terms. Let's see. Okay, psi 2. The first term is V2. That's the long channel solution. And then you have the second and third. That's the short channel solution. So the long channel solution is this one. That's we can write this down by depletion approximation. Okay, the psi s, the x equal to 0 is psi s. That's the particular gate voltage will have a surface potential, and then it goes to and this parabolic curve with apex as equal to x to WD or diffusion depth. But the second and third term combined, B2 and C2 combined, is the short channel effect. So if it's long channel, then the SC is negligible. Then you have the potential here. But when the channel is short, this will add to the potential. That makes the potential higher. So the channel length dependent part is given by the second and third term combined. And now there's a little bit more math down here. Okay. Now for sinh, by definition is that. So if z is positive, you can approximate by only the first term, e to z over 2. Then the sum of the sinh divided by sinh, okay, can be approximated by the exponential. And okay, and then let's see. Yeah, so this is coming here. So one is going. Okay, this one is maximum at the source, y equal to 0. It goes down toward the drain. This one is 0 at the source, but goes up toward the drain. But when you add them up, there's a minimum point. Okay, apply this. So the square root of the product of these two terms is here. So in other words, the potential, the potential is a minimum, which means the barrier as a maximum. So we come back to this schematic. Okay, so this it means that the potential between the source and drain, you have the B term and the C term, and they have a minimum or maximum barrier given by the square root of the product. Okay, so now the square root of product, see, this is e to the pi L over 2 lambda, and then down here you have pi over lambda. So this becomes e to the pi L over minus pi L over 2 lambda. So this means that the maximum barrier, which mainly controls the current, that's the exponential minus L over 2 lambda point. Okay. And also we can see that when lambda goes down, this term goes down, because when lambda goes down, 1 over lambda goes up, but e to the minus 1 over lambda n goes down. So all these terms will be dominated by the longest term, lambda 1. Okay. Lambda 1, we call it the scale length lambda. Okay. And let's see, go back here. Move on. There are more math details in the book, in the Word file I posted on the website. So that the minimum, we call it Y minimum, the minimum potential or the maximum barrier, is this dependence. Okay. And then for B and C, that's solved from the more detailed boundary condition. Let's see. Okay. B and C are solved by requiring the psi2 to satisfy the source condition when y equal to 0, and drain boundary condition when y equal to L. Okay. So with that, you can express the square root of B21 and C21 in this form, with 8 over pi here. All the rest are the same. So this model gives this second term as the short channel effect. And we will estimate the value of the so this exponential e to the minus pi L2 lambda. But this factor is on the order of 1.5 volt. Okay. Psi bi is about 1 volt. And psi s is probably close to 1 volt as well. And VDS, let's say VDS is 1 to 2. So when the magnitude of this term is about 1.5. Okay, now, if the short channel effect is 1.5 volt, then it's too much. So this term has to be much less than 1. Okay, so which means that we want the short channel term, the whole term, to be, let's say, less than 100 millivolts. Okay, so we need to keep L larger than 2 lambda. If L is larger than 2 lambda, then this will be smaller than e to the minus pi. E to the minus pi is about this number times 1.5 volt, and the product is less than 100 millivolts. Okay, so it's very convenient result from this model is that the minimum channel length is 2 lambda. Okay, if L is smaller than 2 lambda, then this term will become more larger than tens of a volt, and we consider that it's too much, to excessive short channel effect. Yeah. So all this boils down to what's the lambda. Okay? If you know lambda, then you know when the channel length becomes too short, and then this term becomes over tens of a volt, which will have a very large effect on the threshold voltage. Okay. In other words, if we go back to the short channel roll off, so L equal to 2 lambda is somewhere around here when the threshold voltage becomes starts to go down with shorter channel length. Okay. So this problem is now simplified to find out what the lambda is. Okay, so we go back to the lambda equation, or the scale length equation. Okay. This equation was derived from the dielectric boundary conditions. Okay. The solution is plotted here for different dielectric constant ratio. Okay. SL2, this ratio is 1/3. That's this curve, and 1 means that assume that the permittivity are the same. In that case, we have tangent plus tangent equal to 0, and that's the straight line here. A very simple result. And so, so first, let's observe some key features. Okay? So first of all, the solution of this scale density equation is plotted in dimensionless scale in here, and the solution is always satisfied, which means that lambda is larger than WDM, and also is larger than Tox. In other words, the scale length lambda is larger than the larger of Tox and WDM. And that's because when you have a two tangent add up to 0, that means one angle is in the first quadrant, and the second angle, the other angle is in the second quadrant. Okay, so one tangent is positive, the other one tangent is negative. But and furthermore, if the direct constants are the same, you have two tangent add up to 0, then basically two angle add up to pi. Okay, so if this angle plus this angle is pi, then the solution is lambda equal to WDM plus Tox. That's this line when this ratio is 1. Okay, so this is this simple result. We can go back to the MOSFET, the short channel MOS schematic. Okay. Let's see. Let's use this one. No, it's this one. Okay. So this is a two-region model, but if they have the same direct constant, essentially is one region. Okay. In that case, the lambda is basically the height of this rectangular box, WD plus Tox. Okay. And the minimum channel length is twice the height. So L minimum is 2 WD plus Tox. In other words, the aspect ratio of this rectangle determine the severity of the short channel effect. Okay. And okay. That's here. And when the epsilon, when the ratio is not 1, it's just mathematically just effective height for the two-region case. Okay. And furthermore, we notice that there's a symmetry point here. At this point, the solution to this equation is independent of epsilon ratio. Okay? And that's because both angles are close to pi over 2. That means the tangent is going through a infinity, a divergence, singularity. So if one angle is a little bit less than 90, that's positive infinity. The other angle is a little bit larger than 90 degrees, that's minus infinity. So they always cancel out because of that constant. That's this point here. But the solution we are looking for needs to be at the lower right corner. And the reason is that, remember the M factor. The M factor is 1 plus 3 Tox over WDM. 3 is the ratio between the permittivities. Okay? So in other words, the oxide has to be thinner than the diffusion width, which means the upper left corner is not acceptable, only the lower right corner. And for the lower right corner, you notice the dotted line solution. Okay? So in the lower right corner, we go back to the tangent. Okay? In that corner, this angle is very small. This angle is close to pi. Okay, so we can make approximations. This is linear tangent theta equal to theta. Okay, this is tangent pi minus theta equal to minus tangent minus theta. Okay. If you apply that, you obtain this lambda equal to WDM plus the permittivity ratio times Tox. And that's the slope shown here. So for high K gate insulator, okay, high K means this ratio is small. So that helps. Okay, for a given WDM, the high K will drop the second term, which means that the scale length is shorter, therefore the minimum channel length is shorter. Okay, so this already helps, but only to some extent, because that's only the approximation near this corner. Once you go away from this corner, it's no longer a straight line, except this one case. Okay? It actually bends. Okay? So, in fact, we look at this very high K case, 10. 10 means that the SR2 has a permittivity of a direct constant larger than 100. Okay? But you cannot exceed this point. Okay? This point is T ox over lambda equal to 2. In other words, to be on the lower side of this center, lambda needs to be larger than lambda is larger than 2 T ox. Okay. This means that if you have a really very high K, then this is no longer valid, because you are no longer at the lower right corner, but rather it's limited by the whole curve. Okay, so once you are in this limit, then this is given by the physical thickness of oxide, regardless of the dielectric constant. So for very high K, the limitation is given by this through 2 T ox. Okay? And the physical implication is that when in this corner, this is due to the vertical field. For the vertical field, we have the dielectric constant. Let's go back to when oxide is thin, it's limited by the vertical field. But when for high K, the oxide can be very thick. In that case, it's the lateral field. For the lateral field, there's no dielectric constant. That dielectric constant doesn't play a role. So the physical thickness has to be controlled. Yeah. So that's what this comment at the bottom is. If the K is so high that actually the lateral field is the limiting factor, then the lambda is simply given by the physical thickness of oxide, okay, regardless of K. Okay. So in this case, this model we go to 2. In the beginning, we go to 2 region. 2 region scale length model. Okay. If it's 1 region, then you only get this result. But the 2 region shows that that's not a whole story, especially with high K insulators. All right. But the bottom line is that, go back to here, the lambda is larger than the larger of WDM and TOX. So we thin down the TOX side to scale the short channel device, but we also need to reduce the maximum diffusion width. And this means that we have to increase the doping, because in chapter 5, or actually chapter 4, the maximum diffusion width is given by at the 2 side B condition. Okay. And if you plot that as a function of the substrate doping, we have this 1 over square root of NA dependence shown here. Right. So to reduce the diffusion width, the substrate doping must go up as the square of the channel length. Okay. So for example, you want to go from 1 micron to 0.1 micron. The doping the concentration has to go up by a factor of 100. And go another from 100 nanometer to 10 nanometer, the doping has to go up by another factor of 100. So it becomes 10 or 19 or above. And that will have a problem that we'll discuss in the later part of chapter 6. Okay, so this is the short channel effect. The other effect is called velocity saturation, as shown here. Chapter 5 says the long channel, the VD set is Vg minus Vd over n. But for short channel, it's much less. Okay, if you try to scale that. That's because the velocity for short channel device has reached the saturation value. Okay, so that first of all, the ID set is much less than the long channel value. Secondly, the saturation voltage is much lower. In the long channel case, it's almost 2 volts. In short channel, it's only slightly over 1 volt. Another factor is that the current, it's no longer Vg minus Vt over square. It's more like linear, and it no longer has the 1/L dependence. Okay, so we need a different model for the velocity saturation case. Typical velocity field relationship is shown here. This type of expression is empirical. Basically, that it adds for the low field is velocity equal to mobility times field, V equal to mu e. For high field, we add a denominator term that it's 1 when the field is low. Okay, so that's the omega region. But when field is high, the 1 becomes negligible. Then the velocity reaches mu effect times EC. EC is a constant we call the critical field. This critical field is basically V set divided by mobility. Because when E is very high, the denominator becomes E over EC. And so the E will cancel, and then V equal to mu effective V set equal to mu effect times EC. The factor n is a measure of how fast the carrier velocity saturates. Okay, the larger the n factor, the faster it saturates. Okay. Usually, electron has a larger n than holes empirically. But we only solved n equal to 1 case because that's the only case that's easy to solve. N equal to 2, you need to solve numerically rather than analytically. It's in the book. Here we only covered n equal to 1 case. The picture is the same. So for n equal to 1, current emerging charge density divided by area times velocity. Okay, and this velocity, instead of mu field, it becomes mu field with a denominator 1 plus that. So this is the field is replaced by dv dy. Okay. Now, strictly speaking, this is not a field. The field is the d psi dy. Okay, but V is the Corsi Fermi level. Okay. But mathematically, it's easier to solve because you only have to change the current density equation here. Okay. In fact, you can argue that the so-called driving force should be the dV dy instead of the electric field d psi dy, because d psi dy only give you the drift current, and dV dy give you the drift plus diffusion current. So in any case, so we multiply the denominator to the other side, and keep in mind that IDS is a constant because of current continuity. So it's constant between the source and drain. So we have two terms on the left, and then we moved dV dy back to the right side, and we can solve dV dy like that, but with the IDS factor here. Now we can multiply dy over and then integrate on both sides. IDS is constant, so integration with dy is simply multiplied by L. In this side, integration with dV is simply multiplied by VDS. In this case, we have an integral of a QI dV. And then after integration, you move the IDS term back to the left, to solve IDS. So you end up with this equation. Okay. So for n equal to 1 velocity saturation model, the current is given by that. The numerator is the long channel, or is the without velocity saturation. Okay. And we derive this. So velocity saturation, add this in the denominator. Okay. And you can see that if V set is infinity, that's just 1. So you back to the long channel case. Okay. Furthermore, we apply this QIV equal to Cox Vg minus V minus MV that we applied in chapter 5. So we put this in here, and then we can integrate. Okay. So IDS for n equal to 1 velocity saturation model becomes that. And the only difference is the vector here in the denominator. Okay. If this is negligible, then we back to the long channel, the constant mobility case. But this means that there's a VDS dependence. Okay. So when we try to find out the VDS when the current saturates, we have to take this denominator VDS dependence into account. Okay. So we find out VD set by solving this equal to 0, and it becomes this expression. It's not simply Vg minus Vt over m because of the VDS dependence in the denominator. Okay, but you can still see that if V set equal to infinity, that's 0. So 1 plus square root of 1 is 2. 2 and 2 cancel. So Vg minus Vt over m is the long channel case. And you put this back into this expression to find out the saturation current. And that's given by this part. Now there are two limits for this case. In the long channel limit, okay, it's when this is much less than that. In that case, the numerator here has to expand to using a power series to have the zeroth order term and the first order term, because it's 1 minus 1. So the 0 order term will cancel. You have the first order term left. But in any case, it recovers the long channel saturation current, mu Cox W over M, L, Vg minus Vt squared over 2m. Okay. So this is the long channel case that we are familiar with. But in the short channel limit, okay, short channel limits, let's say L equal to 0. if L go to 0, then this ratio is 1, because that means this is very large. So infinity over infinity, that's 1. So you only have the factor in front left. And this is so-called velocity saturation limited current. You can see that it's a very simple expression. Cox times Vg minus Vt, that's Qi. So it's W Qi Vset. Okay. So that means that even at the source, the velocity is already saturated. Okay. And so that's in this case, that's the highest current you can get, regardless of the channel length. Okay. But apart from that, let's go back to the general expression. For the general expression, if you look at the drain end of the channel, okay, you can show, okay, you can show that the Qi, okay, remember Qi is given by that, okay, given by this, and you can show that ID set is WV set Qi, which means that the carriers are moving at the saturation velocity at the drain. Okay. So the reason that the current reaches the maximum at the ID set is because the velocity at the drain reached the V set. Okay. But we go back to this expression. For V equal to V set means that E is infinity. Okay, so only when that's the highest you can get, the asymptotic value you can get is when E is very high, going to be set. So this means that at the drain, now notice that, okay, notice that in the long channel case, we say it's pinch off, right? Pinch off, if Qi go to 0 at the drain, then the velocity go to infinity, which means dV dy go to infinity. But for velocity saturation case, the Qi is not 0, Qi at the drain, and so it's not pinch off. But nevertheless, the velocity equal to V set, which implies dV dy also equal to infinity. So that means the GCA model will break down. And so far we followed the GCA model. So now we need a long GCA model, like what we have described in chapter 5. And that model is shown here. GCA is without this second term in the inversion charge. Non-GCA, we have the first term is the gate-induced inversion charge, but we add a second term due to the Y curvature multiplied by the n equal to 1 velocity field relationship here. Okay. And the solution is shown here. Without this term, the GCA is this dashed line. So it goes to peak, the peak given by this. After that, it goes down, which of course is unphysical. That's because there's a second term that supplies the inversion charge. So if you include this non-GCA term, then the curve becomes continuous with a positive slope. So the current still go up to saturation, but much slower. So this shows that in the velocity saturation case, the non-GCA model has to be implemented. to get a correct IV curve. Okay. I'll talk for a few more minutes, and then we take a 5-minute break before the exam at 11. Okay, now, so far, we are still under the regime, under the regime of Triffin diffusion model. Okay. Triffin diffusion means that the carriers are close to thermal equilibrium. And so we can apply the Fermi-Dirac distribution function. But when the MOSFET is very short, it's only a few mean free paths, because to reach the thermal equilibrium, you need a collision between carrier and the lattice. And that means the mean free paths. There has to be a lot of many mean free paths between source and drain. But mean free paths can be as long as 10 nanometer. Now, if the channel length in this shown here is only 30 nanometer, then you don't have enough collisions between the source and drain to bring the carrier into thermal equilibrium with the lattice. So in that case, we can see in this case, this is so-called Monte Carlo simulation. Okay. With Triffin diffusion, we assume that the carrier, this is the conduction band. Okay. This is conduction band. Each particle, each sphere represents maybe 1,000 carriers or 10,000 carriers, whatever that is. And in the Triffin diffusion model, the carrier are supposed to take the lowest available state, which means right above the conduction band. And there's no state in the gap, of course, but once you're above conduction band, there are lots of states. But in this case, you can see that the states are actually empty because there are no carriers. The carriers are occupying the higher energy states. Okay, so this is not in thermal equilibrium. We call these like hard electrons. This happens when there are not enough collisions or not enough mean free paths between source and drain to apply the Triffin diffusion model. In that case, we have to solve the so-called Boltzmann transport equation, which is a very mathematical, tedious solution to solve a partial differential equation to solve the distribution function. The only distribution function we know is under equilibrium, is the Fermi-Dirac. Okay, but this is not valid in the case of a very short device, where the carriers are not in thermal equilibrium with the lattice. In that case, we have to solve the Boltzmann transport equation. And in one of approach, we call the Monte Carlo simulation. That's what generates this plot. Okay? But allow you to look at the physics. If you look at the transport equation, basically says that for a carrier from an initial state to a final state, means that the initial state is occupied and the final state is empty. Okay, instead of going to the lowest empty states. Yeah. And if you allow this, then we have the so-called velocity overshoot. In other words, for the carrier near the drain, those are no longer following the velocity saturation model, because velocity saturation model, let's go back to that. Okay. This assumes, this actually is due to the electron and optical phonon collision. But if there are not enough collisions, then the velocity will not be saturated. And that's so-called velocity overshoot effect. And indeed, we can see that the from a Monte Carlo solution, we can see the electron near the drain can exceed 10 to the 7. Okay, this is 30 nanometer channel length, which is 2.5. And okay, so in that case, how do we predict the current when the driven diffusion model doesn't apply anymore? And okay, one of the clue here is that you can see that even though the drain it can go to very high velocity, but at the source, it's only a little bit higher than 10 to the 7. So even in this case, when the velocity is very far exceeds the VSAT at the drain, but current is still not much higher than what's predicted by the velocity saturation model. Okay, because at the source, the velocity is about 1.2, 1.3 times 10 to the 7. Okay, so I will stop here, and then you guys take a 5-minute break, and then do the midterm exam, or pick up the rest of chapter 6 next Monday.
OK，谢谢。